From stalactites to clouds to most organic reactions to how an enzyme can pluck exactly the right molecule out of your blood, reversible reactions are key to understanding most chemical processes. But most people don't really understand how they work, and that includes many professional chemists. Well, the good news is I can fix that with just a couple of dice and some game counters. Let's find out how. If you've ever learned about reversible reactions, you'll know, of course, they're reactions that can go forwards and backwards, and that given a bit of time, they'll reach an equilibrium where the concentrations stop changing. And you might know that a simple number called the equilibrium constant tells us what the concentrations will have to be at equilibrium. And what that means is, if we take away some of the product from the equilibrium mixture, the reaction will go forwards to make more product and get to equilibrium concentrations. But if we add more product, the reaction will go backwards to make more reactant, and once again get back to concentrations that fit the equilibrium constant. At least that's how it's usually explained, but it's not really true. You see, the problem with this simple explanation is that it sounds almost as if the reaction mixture knows what to do and is actively switching between the forward reaction and the back reaction just to fit some calculation. And it really confused me when I was a student. How do chemicals or molecules know what to do? And why do they care what the equilibrium constant is anyway? Well, they don't. And they don't. As I've already told you, we can see all the same behaviour using these two dice and some game tokens. You see, what we're really talking about is something called a dynamic equilibrium. Dynamic means if we look at the details, everything's still moving. But equilibrium means that if we zoom out and look at the whole thing, the big picture isn't changing. Huh? Let's take a look. So here I've made a track with 2 columns and 36 rows. And this column will be for yellow tokens and this column for red tokens. And I'm going to roll these percentile dice, and whichever row they choose, in this case 42, the token in that row is going to change colour. Now, I considered using 3 6-sided dice to get a number between 3 and 36, but that method has a serious fundamental problem. And if you think you know what it is, why not post it down there in the comments? So at first, yellow has got 36 tokens and red has nothing. So at the beginning for our first turn, we must be changing a yellow token into a red token. So let's try that, and we get 3. So row 3 is going to change into a red token. So now let's just do a bunch more. Now after 10 turns, we've only got 8 red counters, and that's because red has already started going back to make yellow. And in fact, that first happened on the 7th turn. Okay, let's keep going. So now we've arrived at an equal number of tokens on both sides. There's the same chance of tokens flipping either side. We are going to stay at roughly this number of tokens now. This is the equilibrium distribution. But when we look at the individual tokens, we'll see they are still moving. I'm going to keep rolling this a bit more just to show you the graph, and you can see what it looks like. This graph shows how many yellow tokens we have for each roll of the dice. And you can see that the amount of yellow changes at a very high rate at the beginning, but flattens into a sort of flat line. It doesn't look nice and smooth because there are only 36 tokens of each colour. So let's run a computer simulation with 100,000 tokens that works exactly the same way. And now everything starts to look like the nice smooth graphs that we get in chemistry. The shape of this graph makes sense because when we start, all of the tokens are yellow. So yellow token is changing sides almost every turn. But as we lose yellow tokens, the chances of the dice picking yellow get steadily lower. But on top of that, as we create more red tokens, the red side starts turning back into the yellow tokens that we've lost. And of course, everything works the same way for the red side, but from the opposite direction. This means that the dice game will always end up with a roughly 1-to-1 ratio of yellow and red tokens, however many tokens you start with. And that's exactly how a dynamic equilibrium works. Once equilibrium has been reached, it's dynamic because as long as I play the game, the tokens are still changing sides. But it's an equilibrium because the total amounts of yellow and red don't change significantly. And we can calculate an equilibrium constant from this simply by dividing the number of red tokens by the number of yellow tokens, which in this case, of course, will be about 1, because the chances of yellow turning into red are exactly the same as the chances of red turning into yellow. Now, if we want to get an equilibrium constant that looks more like the ones we see in chemistry, we can just make the probability of yellow turning into red different to the probability of red turning into yellow. To do that, let's add a dice roll to every turn. So instead of automatically switching a counter every turn, we're going to roll this 20-sided dice. A yellow token will change sides for any roll from 1 to 18, but a red token will only change sides on 19 or 20. But this game will take forever with real dice, so here's a computer simulation that works exactly the same way. And here are our curves. It's exactly the same game, but we've just changed the chances of a token flipping to make it easier for yellow to turn into red than for red to turn into yellow. And that means that with 10,000 tokens, after about 50,000 turns, we settle at the equilibrium ratio of 90% red to 10% yellow. And sure enough, we get the same ratio even if we start with all red. And we can also drive the equilibrium, where we remove the product as it gets made. Then all of the reactant turns into product. Ta-da! That's it! That's how a dynamic equilibrium works. None of the tokens know or care what the ratios are supposed to be. They just end up in those ratios because of the statistics. We never have to stop to count them and change the tokens if the numbers aren't right. It's just yellow making red and red making yellow, with the equilibrium constant being the difference in how easily yellow makes red divided by how easily red makes yellow. What's that? What about resisting changes to pressure and concentration? It can do that too. But before I show you, I just want to tell you that this video is produced at Kyushu University. It's one of Japan's top universities, and we have courses in science and engineering in English. A great alternative in these uncertain times. So check out the link in the description. Now, if we want to add in things like concentration, it's better to use a two-dimensional grid. And instead of having one token simply turn into another token, we're going to model a reversible dimerization reaction. For example, where two NO2 molecules dimerize to form N2O4. And N2O4 can break back up into two molecules of NO2. So in our game, we are simply going to have double pieces that might split into single pieces, and single pieces that, if they meet, might join to make a double piece. They're going to move randomly around the board, and we're going to pick one piece at random every turn. If it's a double piece, we're going to roll a dice to see if it splits up. And if it's a single piece, and it's next to another single piece, we're going to see if they join to make a double piece. This would take forever with real dice, so we're going to use a computer simulation all the way this time. But the rules are exactly the same as if we were physically rolling the dice. So in this simulation, we're going to use a grid with 100,000 squares and start with 1,000 double pieces. Now we can calculate an equivalent to pressure or concentration by counting the number of pieces per square. So in this case, our concentration starts at 0.01 pieces per square. I made this program in Python, and it can show me a simple display of the grid with dots for each square and a D for double pieces and an S for single pieces. Now, the speed of molecules moving is much faster than the rate of reaction, so instead of carefully moving the tokens, we're just going to randomize their position every turn. And let's start off with equal probabilities of reaction of 50%. So, what do you think will happen to the numbers of the counters? Remember, we started with 1,000 doubles. What do you think the line on the chart will look like? Well, let's run the simulation and find out. So here's the plot. You can see we have the same general features of the simple two-track game, but now we end up with more single pieces, even though the probability of reaction was the same. And as we expect for a dynamic equilibrium, we finish with the same concentrations whether we start with all double pieces or all single pieces. But what happens if we change the starting concentrations? Well, this is double and quadruple the original concentration, and this is half and a quarter of the original concentration. The ratios of doubles and singles are very different, but there are always more single pieces, at least in this concentration range. So what's going on? Remember, the double pieces can split into two single pieces at any time, but the single pieces have to be next to another one to have a chance of joining up. That means that the overall probabilities of changing aren't the same for double and single pieces. Reducing the concentration of pieces doesn't change the probability of a double piece changing each turn, but it makes a huge difference to the single pieces. As the total concentration is reduced, it's much less likely for a single piece to be next to another one. And that makes the total rate of change much lower for single pieces than it is for double pieces. So this means that lowering the concentration increases the relative proportion of single pieces. But there will come a point where the number of pairs of singles will equal the number of doubles. And at that point, the singles will turn into doubles at the same rate as doubles turn into singles. And we've returned to equilibrium. But remember that it's a dynamic equilibrium. We're still rolling the dice every turn. Pieces are, or are not, changing every turn according to the two simple rules. Now, these graphs might make some of you feel a little uncomfortable. Isn't there supposed to be something that stays the same here? Some sort of constant? But when we look at the numbers of pieces, we can see that the ratios are very different at different concentrations. Well, that's because it's not actually simple ratios or numbers that we care about. Let's try calculating a number the same way that we'd calculate an equilibrium constant. And let's say our forward reaction is going to be the double piece splitting into two single pieces. So now, an equilibrium expression would look like this. It's the concentration of single pieces squared divided by the concentration of double pieces. And what results did those calculations give us? Well, starting from 0.04 pieces per square, we can halve the concentration, and again, and again, and again. And we get the same value, 0.013 pieces per square. No matter what the total concentration of pieces is, or how many of each kind of piece we start with, or whether we're using bigger grids or smaller grids, that number stays the same. In other words, it's a constant, just because of some dice and our two simple rules. Pretty cool, huh? If you're impressed, clicking the like button will help me make more videos. Thank you. But why does the chemical equilibrium expression work for this simple dice game? Because the rules are the same. N2O4 molecules can break up at any time, but NO2 molecules have to meet each other before they can react. That's it. That's all it is. Now, I've made a video about the equilibrium expression that explains exactly why we always end up with this kind of relationship. So check it out if you want the details. And with this game, we can even see how equilibrium mixtures resist changes in pressure. Let's start with a 100,000 square grid, with a total pressure of pieces about 0.027 pieces per square. And we're going to compare this equilibrium mixture with an inert gas model. In other words, our inert gas pieces can move about, but they never react, while our equilibrium pieces can move and react as they did before. Now, let's decrease the size of the grid to 1/20th of its original size while keeping all the pieces on the board. Of course, that's going to increase the total pressure of the pieces, right? Because there are far fewer squares for every piece. So, if we shrink the grid to 1/20th its original size, the pressure of the inert gas pieces must become 20 times higher. But the pressure of the equilibrium pieces doesn't grow as much. That's because the single pieces will meet each other more often on the smaller grid. So they'll combine into double pieces more often, and that removes pieces from the grid, and that reduces the pressure. And the opposite thing happens if we expand the grid 20 times. Because now it's harder for single pieces to meet each other, while the double pieces are still splitting up and generating more single pieces. So the pressure of the equilibrium model remains higher than the inert gas model. In other words, it looks like our game pieces are trying to resist changes in pressure. But we all know, don't we, that these plastic tokens aren't trying to do anything. It's all just because of dice rolls and two simple rules about joining and splitting pieces. So, these counter games demonstrate three things. 1. Nothing knows what it's doing or what it should be doing. 2. The equilibrium arises because each process, the forward and the back process, slows itself down but speeds up the other one. And the third point, and this is really important, the final equilibrium state, the concentrations or the pressures, is all a result of the fundamental properties of the system. In the 2D grid game, the final equilibrium state depends only on the initial pressure of pieces and the probabilities of reaction. And in chemistry, the final equilibrium state depends only on the initial pressures of molecules and their probabilities of reacting. And nothing is trying to do anything, whatever the famous Le Chatelier principle might have had to say about it. But on that point, what did Le Chatelier really say about chemical equilibria? I'm making a video about that right now, so be sure to look out for it. And if you know of any interesting examples of a dynamic equilibrium that isn't chemistry based, I would love to see them in the comments. And I'll see you next time.